Okay, students, hang on to your hats. 'Cause here we go. This can get pretty deep right here. And truly, in my way of thinking, this is very advanced for a Chem 1 course. But we're going to dive on in. And this requires you to really think in terms of spatial theory. You got to be able to picture what's going on. And when we're talking about orbitals and shapes, please keep in mind that you're thinking about, you've got to imagine maybe a fly buzzing or a wave. That's what you really have to think about, is a wave, an ocean wave perhaps, rolling up onto a beach. That's the wave pattern that electrons make. Electrons don't travel like a fly buzzing unless it's a super fly buzzing super fast and making more like a wave or a cloud in its wake. Like imagine, if you would, a mosquito truck with a fog behind it. That's sort of what electrons leave in their path. They're going so fast they leave like a fog or a cloud of charge behind them, just trailing in their wake. But they're not traveling in a straight line. They're traveling like a wave. And they make these shapes. And the shapes that they make, remember we discussed in chapter 6, they make a sphere shape. Those are called s orbitals. They make those peanut shapes. Do you recall those? Those are p orbitals. They make those d shapes. Those four-leaf clover type shapes, those d orbital shapes. We're going back to those. And then what happens when those interact with each other? That's called hybridization, and that's where we're going a little bit in this section, and the next couple of sections. And what about when you have two atoms that bond together covalently that share their electrons? What happens as those electrons are moving between those atoms now? What happens to those shapes? As their electrons are moving in these waves of negative charge, what happens to that then, and what does that look like? That's what this is talking about. So let's talk about the valence bond theory. According to this, atoms share their electrons in orbitals. Remember what orbitals are. Those are the shapes that they make, electrons make, as they're moving around the nucleus. Sometimes those shapes are sphere-shaped like a ball. Sometimes they're those peanut shapes. Okay, but as they are being shared between two atoms, they begin to overlap each other. When you have one electron from one atom sharing with an electron from another atom and they overlap, that's the valence bond theory. Okay, that each of those overlapping orbitals has one electron in it that's unshared, and they're spinning in opposite directions. Please keep that in mind. That's the valence bond theory. Now we're going to continue this on. What if you have two electrons being shared? So a pair being shared. That's what holds your electrons, your atoms together. Here's an example. Okay, here we have hydrogen. Hydrogen has its single electron, which means it's in an s orbital, which we know because it's in group 1. In group 1, all of their electrons have one one electron in their valence shell. So when they overlap, since their electrons are in this first energy level, and they fill an S-shaped orbital, they make this round sphere shape as they're moving around. When they overlap, this might be what its shape looks like when they're sharing. And so they make this kind of shape that looks like eyes looking at you when they're sharing their overlap, their orbital overlap. Okay, got that picture? But what happens when you have p overlaps? All right, this, by the way, is in your textbook. This one in particular when it's the first one I showed you was 2 hydrogens sharing. What about if it's 2 fluorines, like on page 376? That would be the case of this second one right here. If you have 2 fluorines, they each have 7 electrons. They need 8. So in this case, they're in the p orbitals. P, they kind of look like peanuts or dumbbells. So when you have those two overlapping, notice what that looks like. And how that this would be right here where the electron overlap would be occurring. But what if you have something like HF, where you have a hydrogen atom with its 1 electron and a fluorine atom with its 7, and now they're sharing 1 electron each, so they're sharing a pair of electrons between them. What would that overlap look like? Okay, according to the valence bond theory, that overlap would look like that, and each of them sharing that space. Okay, but that I'm not going to get into these bond lengths and bond energies, but it does have some issues and some problems, because we know that it does explain some things, but it doesn't explain everything. And what about experimentation? Experimentation, here's some beautiful pictures that show how this could happen. And right here is a sample problem that I would want you to go through, that's at the bottom of 378. Okay, it's talking about what would the bond angles be, and then I would ask you, it's talking about which is going to have unshared electrons, and where would the overlap be, and how many bonds would they form. Okay, but I want us to instead go to hybridization. Okay, because experimentally, the valence bond theory just doesn't explain everything that it needs to explain. And so it's found that, especially with S's and P's, most especially S orbitals and P orbitals, they don't just stay in their own little spaces and overlap. They mostly join together, kind of squish together into one big hybrid space. And that's called hybridization. Hybridization of orbitals. And we're not going to spend just a whole lot of time on this topic because, again, it is a little advanced for Chem 1. But in this case, we see, as on page 379, what if you had beryllium chloride? You had beryllium with its 2 electrons, and you had chloride. We find that what actually happens here is that the S's and the P's, they kind of squish together to form a hybrid, and that hybrid is called an SP. And you see the yellow S in your textbook. If you'll read through these pages, I would strongly encourage you, especially sections 9.3 and 9.4, to read those sections. And in section 9.3, it explains to you that in this text, the yellow balloon shapes, these are going to be used to represent S orbitals. The blue will always be used to represent P orbitals. And the darker shapes are going to be used to represent orbitals that contain electrons. And that if they're clear, more clear, almost white, that means they are empty, that they don't have any electrons in them. Okay? And what these two do when they join together and they squish themselves together, yellow and blue make green. So this is called an SP hybrid. It's got properties of both. There's your sphere and there's your peanut. And so they kind of join together and make this funny looking shape. But please, students, I'm asking you to keep in mind what this means. What this means, remember, think about the mosquito truck, okay? When these electrons are moving, they are moving through space. Put your hand in the air and move through space. They are generating this shape of a cloud. So that mosquito truck spraying its fog around is an electron making this shape as it moves itself around an atom. This is kind of the shape that it makes as it's moving. Okay? This is not a enclosed bedroom space. This is the shape that of the path that an electron takes. And it has been determined and backed up through mathematical calculations and experimentation. It is a theoretical, mathematically substantiated thing. Okay? It's a path that the electron takes. Please get that in your head, please. Okay? That's important for you to understand. This is called an sp hybrid. It's a hybrid orbital between an s orbital and a p orbital. When they squish together, and instead of having a separate s orbital and a separate p orbital, they join forces and become a hybrid orbital, sp. And you'll notice on top of page 381 what they can look like. They can look like this one that's on this page. Here is what beryllium might look like, and beryllium chloride might look like as it shares. The beryllium is your central atom and your two chlorides on either side of it, and you have s orbitals joining together with p orbitals and hybridizing. Notice they're the green ones because yellow and blue make green. Keep in mind that these white ones or these clear ones mean they are unoccupied. No electrons are in the clear ones. Read section 9.3 in your text, and it will tell you. That's what that's talking about, okay? So now they can be hybridized or joined together. Those S and P's can kind of squish all together and form hybrid orbitals, okay? And this is what it would look like. This is a hybrid orbital of where you have the, I'm waiting for the screen, it's coming. Here you see the beryllium in the middle and the two chlorines. Here is where it's showing you what's happening. You have your s orbitals from your beryllium and your p orbitals from your chlorine, and they're all squishing together and kind of intermixing with each other to form this hybrid orbital. That's called an sp orbital, and it's called an sp2 in this case because you have one s orbital and two p orbitals involved in this. Okay, it's a two. It's a that 2 right there means it's the second energy level. The s orbital that's in the second energy level, and then two p orbitals. Those two p orbitals are where your chlorines live. Okay, think about the electron configuration for chlorine. Its valence electron configuration is 2s2, 2p5. And so we're going to squish together the s orbital and the two of the p's, and when they all come together, it makes that sp2 hybridized orbital. That's what it looks like when you put an s and a couple of p orbitals all together and squish them, hybridize them, all right? And when you put it in 3D space, you get this bottom picture. Remember, the clear white one down there in the bottom right corner would be where there are no electrons in that particular one along the z-axis that's coming out towards us, all right? So that is what it would look like in real space. Now, again, I really don't want to talk too much more about any of this because it's really going to get even more complicated than that. Okay, but those of you that are real sciencey people and you want to read more about it, you continue to read because the pictures are really lovely. Okay, you can see here you've got boron and 3 fluorides. Fluorides are in the 2s and the 5p. 2s2. 2p5 again, so you again have s's and p's together. So when they hybridize together, you can see what's going to happen. Okay? In this case, with your boron and your 3 fluorides, you can see how much larger the hybridized orbitals will be, because there are 3 p orbitals involved. You know, remember on the last one, there were only 2 p's involved. So the hybridized, the sp2 hybridized orbitals were smaller. And this one has 3 p orbitals involved in the hybridization, so it's larger. That's why it's so much larger. Okay? All right, so let's, here you have S's and some P's. All right, and again, it talks about how this is going to happen and what the overall shape and how it's going to be mixed together. 1 S and 3 P's and 2 D's. So here you have some D's involved in this particular hybridized scenario going on. Here you got some D's involved here in this case, and so here's what the first one looks like, those green ones there, and okay, but I really don't want you to get yourself too bogged down in that, because again, that's a little bit more advanced than we would need to go. Okay. I do want you to know what SP would mean, and SP2 would mean you have 1 S and 2 P's, and so forth. SP3 would mean 1 S, 3 P's, etc. Okay? I would expect you to certainly know that. In this case, you can see right here in sample problem 9.4, which is on the bottom of page 385, where you have a single S orbital involved and 3 P orbitals involved, then that hybridization is called sp3, because you have 1 S and 3 P orbitals all hybridizing together to make one hybridized orbital. Okay, that's on the bottom again of 385. And it does affect what the bond angle is going to look like. So you can work through that, okay? And then we get to section 9.5, which again, this is even more into it, because this is talking about what if you have multiple bonds. What if you have 2 central angles, let's say. In this case here, you have 2 carbons that are undergoing hybridization. Notice you've got hybridization going on both carbons. So you have sp2 and sp3 hybridization going on. So you would have to consider both and look at this structure, what it looks like, and this is going to make a pi bonds. If you have 2 p orbitals and they overlap, that makes what's called a pi bond. Okay, a sigma occurs when you just, if you'll look with me on page 387, you can read in here, it says when you talking about bonding schemas, the overlap of atomic orbitals or hybrid orbitals directly between 2 nuclei that are involved in bonding, if they share electron density is concentrated between the internuclear axes, they're just called sigma bonds. Okay. However, if it's with the p orbitals, then they're called pi bonds. Okay. So there is a difference between the 2 different kinds of bonding that you're going to need to understand the difference between a sigma bond and a pi bond. Pi bonds stretch over a much longer length of space because they're stretched across the length of the whole bond, whereas sigma bonds are bonded atom to atom. Okay, that's the major difference between sigma bonds and pi bonds. And there's just lovely illustrations in the textbook that show sigma bonding and pi bonding for you. And that's pretty much all I'm going to ask you to know about those two, because again, I don't want you to get too bogged down in this because it can get very hairy in here. Okay, and I only gave you one homework quiz on this chapter, and that's all I intend to give you on this chapter. Okay, but I hope that you can see here on this page, which is, by the way, it explains how you make pi bonds on page 391 in your textbook. But again, we're not going to talk too much about them, all right, other than, there you go. But I hope that you can see on this bottom left picture, I'm going to wait for this screen to catch up with me. Right here on this bottom left picture where it's, there's your pi bond right there, okay? And it shows you how that it's produced. Here is just some summary statements that you need to know about bonding and molecular orbitals. Again, this is getting a little bit advanced for Chem 1, and you're only going to be required to know about the bonds and the hybridization for this chapter pretty much. Okay? You won't be required to know about bond order. I will expect you to know about these pi molecular orbitals and how, see, you have these two pi bonds and how when they share and overlap, it makes that molecular orbital in between them much larger. So it's more stable. The energy level is much lower and it's much more stable. Okay, and that's pretty much all I'm going to ask you to know, except for this very last portion on chapter 6, section 6, I'm sorry, where it kind of summarizes everything on page 398 of your text. Please remember, your lower orbitals are always going to fill first, and each orbital can only hold 2 electrons with opposite spins. And you're going to obey Hund's rule, which says that orbitals of equal energy are each going to hold 1 electron until all of them get 1. In other words, if you have p orbitals, there are 3 p orbitals in each energy level. Each one will get 1 by itself first, and then it will start doubling up if it has to. Okay. And that's pretty much, I'm not going to ask you to do these sample problems, so I'm going to quit right here.